change of plans today. What I think I'm gonna do is go through the lab first. That's not gonna take the whole period, it's gonna take a while, and then. I didn't know that. We're still late. Not next time, right? Because I was talking and it's disturbing. As I was saying, I'm gonna go through the lab today. Kind of give you a clue as to what the reactions are gonna involve by writing the reactants, all 8 on the board. And then I'm gonna give you a bit of a heads up as to what each of the things involved or where the stations will be, etc. As I'm doing attendance, if you could come up and grab one of these. There's 2 changes I'm making to the lab. It says there are 7 reactions, I've added in 8. Also for what's labeled as reaction number 6, I've modified it a little bit, but I'll go through that. After we've done going through the lab, I'm then going to return to section 4.6. I won't finish 4.6 today, but I will finish it Friday. The lab will be Tuesday, and then I think the next time I see you is the following Tuesday, because I don't see you Wednesday. Do I see you Thursday next week?
There's OD day.
OD day.
Is that Thursday or Friday?
Thursday's Friday.
Thursday and Friday.
Actually? No.
I thought it was just Friday.
I thought it was just Friday.
So are we back on the Monday or back on the Tuesday?
Tuesday.
Check the STC
Monday?
app.
That's family day.
Family
Oh,
Day
that's
is
family
Monday.
day on Monday. Yeah.
Right, so why are we away Thursday?
I don't think I think it's just Friday.
Isn't there interview? There's interview.
Thursday,
That's Friday.
That's right, okay.
Friday is
So I
Pro
see
D
you the
Day.
following Tuesday. That following Tuesday, a week after the lab, will be the review class. Test will be Thursday, okay? So the test will be a week next Thursday. 2 weeks tomorrow. Now, that's definitely not ideal. That'll put us near the latter part of February. Then we have March, April, May, and maybe a week in June. We still have 4 chapters to do, okay? So, case in point, what did we just spend the last 40 minutes doing? Something akin to a preschool activity. And yet, someone downstairs thinks we need to do that every year. It makes no sense to me. And the only thing that I can explain it by is none of the people doing the schedules ever took this course. Or if they did, they have no idea the amount of stuff we gotta get through. Not just in grade 11, grade 12. Like, it's comical if it wasn't so, contradictory to education. So whenever I look at the Knight's Compass and I see that academics at the top, it's like we either got to move that or take it out, because it's certainly not a priority here. And that's not your fault. It's just that you kind of suffer the consequences, because we're not going to finish the course. And given that the course is a prerequisite, when you're done, there may be a very good chance that you don't have all the information you need. So I'll do my best, but, and I've said it for the last 4 years, continues to fall on deaf ears. But nothing bothers me more when we have so much to do and we waste so much of our time. Yeah. Preschool activities instead of school. Anyway, and it doesn't make any difference. So when you hear your name called, come up and grab one of these, and if your cell phone is not yet where it should be, please put it there. Julia, Daniel, Olivia. Samantha, Julian, Claire, Allison. Lauren, Granville, Samantha, Rianne. Nicole, Cassandra, Annika, Christina. Decus, Alexandria, Annabelle, Ryan, and Ariana and Leah.
You cut yourself? Yeah, I did yesterday. Slip outside on the track. Ouch. Feel my ass.
So maybe the first thing to notice is the cautions plural in the margins. So the very first one on the bottom of the first page on the left, most of these solutions are poisonous, corrosive, or irritant. Wash any spills and splashes immediately with plenty of water, notify your instructor. Now that's a general caution. If you turn the page, back of that page, copper 2 sulfate is poisonous. It's a nice pretty blue color, but it's very poisonous. Wash any spills and splashes immediately with plenty of water. I don't anticipate a lot of spills and splashes, given the fact that all of the liquids will be dispensed with droppers. But just be aware that what you're using is poisonous, okay? Underneath that, hydrochloric acid is corrosive to skin, eyes, and clothing. Wash any spills and splashes immediately with plenty of water. So obviously it goes without saying we're gonna be wearing our goggles. The hydrochloric acid we're gonna be using is about 2 molar, which is plenty strong enough to damage your eyes or your skin, okay? What's not mentioned on here is one of the reactants we're using in reaction number 8, which is, there's 8 because I'm adding one, is gonna serve as a catalyst. It's manganese 4 oxide. It's a black powder, but it's a very fine black powder. And you don't wanna breathe that dust up your nose, and that's why when you do that station reaction number 8, you're gonna be dispensing the manganese 4 oxide with a little spatula under the fume hood, in the event that any of that would make its way up your nose. If it does, it turns into a base, strong base, and burns your nose. So, although there will be 1 report per group, there will be 1 data table per person. I do not want the data tables typed, because if they're typed, they're photocopies. I don't want them photocopied. I want them built by hand, with a ruler and a pen, not a pencil, a pen. I want everybody to do their own data table. The reason I want that is because the purpose behind the data tables is if you make one properly, then at least at some level, I'm confident that you know what you're doing. You haven't done a lab like this before. Over the course of the lab, there will be 4 Bunsen burners going throughout the 75-minute period. The copper 2 sulfate is poisonous. The hydrochloric acid is corrosive. The ones that aren't corrosive are toxic. And if anyone doesn't know what they're doing, they're dangerous. The blinds are pretty much almost closed today, but even with the blinds completely closed, a properly adjusted Bunsen burner is invisible. And it doesn't make a lot of noise unless you turn it up really high, but I'm not gonna turn them up really high. Ideally, I'd like the Bunsen burners as far away from the edge of the counter as they could be, but I can't do that because if I push them back from the edge of the counter, the cabinets light on fire. So the Bunsen burners will not only be on, but they'll be near the edge of the countertops, which makes the case for do not bring your coat, do not bring your bag when we're doing the lab. The only thing you need is a lab handout, your data table, something to write with, okay? Even if I sign your data table, if it looks like you don't know what you're doing, I'll ask you to leave, because I don't want anybody to get hurt. Tie back your long hair, don't have loose clothing. If you're walking past a Bunsen burner that's on and you don't see the flame, and you're in a hurry, a whole bunch of bad things could happen, okay? What I'm gonna do now is go through each reaction, each station, by writing the reactants only on the board. Because you're observing the reactions, when you write your lab report up, you should be able not only to generate balanced equations, but give me the states for every participant in the lab, So whatever the reactants were, whatever the products were, and if there's any kind of an energy change. So not just what you see, but what you feel. And notice in the data page, it's before, during, after. So you make observations before the chemicals are mixed, before the reaction occurs, any observations during, and then what look like after. Now, there's nowhere near enough room for you to put all that in the space they've given you. That's just a sample. Take a whole page, okay, and use a ruler. Don't look like you drew it freehand, because if it looks crummy, I'm not signing it. So use a ruler, use a pen, and that's what I want to see when I initially data tape, okay? The stations will probably be arranged sort of clockwise around the room. So station number 1 is going to be over there. 2 is going to be to the right of it. 3 and 4 are going to be close together because they're reversible reactant. It's a reverse of 1. And then 5, 6, 7's probably going to be right back there, and 8's going to be on the side here. So the reactants for number 1. And if you go to, and they're numbered, reaction number 1, adjust the burner flame to a high heat, meaning it'll be invisible. I will do that for you. It'll be right over there. I'll probably move the cell phone tray. It'll be over there. All you're going to be doing is taking a piece of copper. These are crucible tongs. The pieces of copper won't be very big. They'll be like that. And you're going to hold the copper in the hottest part of the Bunsen flame, which is about halfway up the flame. And you're going to hold it in there until you stop seeing changes, and then take it out. The reactants, therefore, in number 1 is just solid copper plus that, okay? And be careful with this one. What type of reaction does this look like it is? Synthesis. Most synthesis are what? Endo or exo?
Exo.
Exo. If a reaction's exo, does it keep itself going? Like a match burning, does it keep itself going? If it doesn't, then it's not exo. So keep that in mind, okay? Reaction number 2, you're going to take an iron nail, and as far as I know, the iron nails I'm giving you are brand new, so there's no corrosion on them. Each group is going to get a test tube rack with 5 test tubes in it. You're going to put the nail in the test tube and half submerge it in a solution of copper 2 sulfate. It's a nice blue color. Okay, so reaction number 2, there's the iron nail, and you're half submerging it in the solution of copper 2 sulfate. Now, the fact that I'm giving you the reactants and the fact that we've studied all the reaction types, you should be able to predict what the products are going to be. I don't need to have all those predictions when you come to the lab, but if you and your partner get together and predict what you should get, that should help you predict what you should see, okay? In terms of the states of the products, you may not be able to do that yet, but once the reaction's observed, you have to do it. And if I see a lab report without states, in other words, if all I see is the states and the reactants, but nothing in the product, I will not mark the lab report. If you have to decide if there's a product that might be a precipitate or not, go to the solubility table. It's on page 373 in your book. We referred to it already. Okay? This is going to take a while. So don't wait till the end of the lab to do station 2, because the longer you let that nail sit in the solution, the better. 20 minutes at least. And make sure you record what the nail looks like before, what the copper 2 sulfate solution looks like before. And then maybe 10 minutes in, what are you seeing? And then after 20 or 25. The longer you leave it, the better. You'll see changes in the nail and you'll see changes in the solution. All right? The next two reactions have to be done in order, 3 and 4. Okay? So you can't start with 4 because 3 has to be done first. The solid compound that I dissolved in the water to make aqueous copper 2 sulfate was copper 2 sulfate pentahydrate. And like any ionic compound, it's a solid at room temperature. And it's going to be sitting at the bottom of a Pyrex test tube to which a test tube clamp will be attached. So there'll be a whole bunch of these at that station. These test tubes don't have Pyrex written on them, which means you can't heat them on a Bunsen flame. But this one does, which means you can. So what you're doing, you're going to take one of these. There will be 2 burners going over there to allow more groups to do this at once. You're going to be heating this over the Bunsen flame. Do not hold, the test tube clamp is kind of spring-loaded. Don't hold the test tube clamp here when you're heating it for 2 reasons. You're too close to the test tube. The heat from the test tube being heated by the Bunsen flame will heat the test tube clamp and it'll get too hot. The other reason is there's a tendency to squeeze this, particularly if you're really nervous. And if you squeeze it, the test tube falls out. So hold it back here, like that. And hold it over the Bunsen flame so that the mouth of this thing isn't facing towards you or anyone else. You're going to heat this thing till you stop seeing changes. Okay? One of the things that'll happen is you'll see a change in color. The other thing that you'll notice when you're heating it is that there's going to be condensation on the inside mouth, inside of the test tube, above the solid. You want to get rid of all of that. It'll take a few minutes. It might even involve you turning it over to heat the other side. And if that means you have to change hands so that you don't face it towards you or your partner, fine. Once you've heated it till no more changes are observed, as you might expect, it's going to be really hot. And hot glass looks just like cold glass. Hot metal just looks like cold metal. So you're going to take this to your desk and then put it on the metal tabletop and leave it until it is cool to the touch. Okay? So, because we're heating this, normally we represent that with a triangle. Okay? What type of reaction would you expect this to be? Decomposition. And based on what I've just described, it's pretty obvious it's going to be endothermic. Until this test tube, after it's been heated, is cool to the touch, you can't do reaction number 4. Reaction number 4 is the reverse of reaction number 3. And what's the reverse of a decomposition reaction called?
Synthesis.
Synthesis, correct. So number 4, every reaction that you eventually write has to be balanced. There has to be states, and if there's an energy change involved, you have to make that observation too. So it's not just what you see, it's what you feel. So after this thing is cool to the touch, probably on the other side of that yellow pillar there will be some small beakers with some droppers, and in each beaker there will be water. Fill up a dropper with water and add water drop-wise to the top of the test tube so that it contacts the solvent. And while you're doing that, observe what you see, but also feel it. It should be pretty clear what type of reaction's happening here. Not just based on the fact that it's a reverse, But remember, reverse is not only in terms of chemical reagents, it's also in terms of energy. Okay? That's reaction number 4. At the beginning of the lab, I will ask one member of each group to put their hand up, and I'll give you a number. What I won't start with is number 4, because this has to be done after this. But that takes a while to cool, just like this reaction takes time to occur. So don't leave this one till the end either, okay? The number I give you will be the station you start at, but after you're done that station, the only order that has to happen is 3 to 4. Do any other one if there's not a lineup. Now, I know with a class this big and with 2 people in each group, there's gonna be a lot of moving around. There still should be no problem finishing this lab in 75 minutes, unless you don't know what you're doing, okay? So besides being dangerous, you're not gonna be a good partner, and then whoever you're working with is never gonna wanna work with you again. That's why I'm giving you the lab handout a number of days before we do the lab. Reaction number 5 will probably be back there to the right of the fan, okay? This one, we're gonna modify it a little bit, only in terms of the instructions. And based on the reactants, you should be able to identify what type of reaction it is. The lab handout says, fill a test tube 1/4 filled with calcium chloride solution. Fill a second test tube 1/4 full with sodium carbonate solution. Pour one into the other. Why? Use one test tube. There's going to be 2 reagent bottles, each with droppers in them. Take 1 or 2 full droppers full of the whatever solution you want to start with, doesn't matter, sodium carbonate or calcium chloride. Add that to the test tube, put the dropper back in the little receptacle in that solution, and then go to the second solution. Do not mix the droppers. And then squirt the same amount of the second solution in here. The reaction will be immediate, you'll be able to see it, okay? And you should be able to tell me what that is, and not only what the products are gonna be, but also the states, okay? Reaction number 6, I'm gonna change it a little bit. Reaction number 6 at the bottom of what's labeled looks like 53. Instead of zinc, we're using magnesium. So you're gonna take, and the magnesium will be all there, it's already cut up. It's little pieces of magnesium that are bent so that they fit in the test tube. Drop it in the bottom of the test tube. Squirt in a dropper full of 2 molar hydrochloric acid. And watch and feel, okay? You probably want to hold the test tube up here and with the other hand feel down here. And you should be able to predict what's going to happen, and you should also be able to say something about the energy change. So in number 6, don't write zinc plus hydrochloric acid, write magnesium. The reason I'm using magnesium is because it's more reactive than zinc, and it will be easier to see with magnesium about the energy change. If the reaction's too slow, you might not notice the energy change as well. Now, what's labeled reaction number 7 is different. I'm gonna add one between 6 and 7, so there's actually gonna be 8, okay? Reaction number 7 will probably be to the left of that big green eye wash station. Okay? There'll be a bottle of sodium carbonate solution and a bottle of hydrochloric acid solution. You do the same thing you did for reaction number 5. Squirt in some sodium carbonate solution, then you squirt in some hydrochloric acid. So the reactants are going to be this. I may or may not give you a bigger test tube for that one. I'll decide before we do the lab. So if you go to your, the test tube racks back there already have 5 test tubes in them, but if one of them is a big one, that would be for reaction number 7, okay? So reaction number 8 is what's labeled reaction number 7 here. Fill a test tube, half fill a test tube with hydrogen peroxide solution. Well, maybe not all the way half, maybe a third. So we're using 6% hydrogen peroxide. You're going to be adding it to the test tube under the fume hood because one member of each group is going to be doing one of 2 parts to this reaction. So reaction number 8, fill a test tube about a third full of this solution, which is hydrogen peroxide. Hydrogen peroxide decomposes, but it decomposes very slowly. So we're catalyzing its decomposition. So put about that much hydrogen peroxide into the test tube, and then, and one member of the group is doing this. Also in the fume hood will be a jar of manganese 4 oxide, which is that finely ground black powder. That's going to be our catalyst. So it's not a reactant. So if you put it on the arrow, it usually suggests it's the catalyst in this reaction. What you do is put the hydrogen peroxide in first, MnO2, manganese 4 oxide. There's going to be a small spatula there. Put about a little fingernail's worth of manganese 4 oxide in the mouth of the test tube. And as soon as you do that, put your thumb over the top of the test tube and then just do this. Don't bash it so hard you break the test tube. Just tamp it down to make sure the solid mixes with the liquid. But keep your thumb on the top because you're going to notice bubbles forming. You want to concentrate that gas in the test tube. While one member of the group is doing that, to the right of the fume hood, maybe over near the sink, there's going to be another Bunsen burner going. That member of the group, the second member, is going to take a wooden splint, hold it in the flame, and let it burn so that, long enough so that when you blow the flame out, you've got about that much of a glowing splint at the end of that wooden stick. You don't want to blow it out right away because you want a good amount of glowing happen. You don't want the flame, you just want the glowing ember. And then the person with the glowing stick and the person holding the thumb of the test tube are going to come together. Put the glowing splint just on top of the test tube. Don't stick it all the way in, just hold it right at the opening. So when you move your thumb and that goes there, that splint should reignite, okay? And igniting a glowing splint is a positive test for oxygen gas. So that should give you part of the clue is one of the things you're going to produce. And they ask you that question then. Okay? When you add the manganese 4 oxide to the hydrogen peroxide, you're going to be seeing bubbles. But don't just look at what you see. Put your hand down at the bottom of the test tube. You may feel something there as well. And if a reaction is endo or exothermic, you should be able to tell over the course of the lab, particularly exo. But if it's not exo, or if it's not endo, don't pretend it is. Don't say you felt something when you didn't. And remember, the lab report that you turn in, one report gets done by 2 people. So each person in that group of 2 has to agree that the answer you're writing there is legitimate. I need a data table from everyone, but I need a report only, 1 report per group of 2. Again, there should be no trouble finishing the lab in a 75-minute period unless you don't know what you're doing. But I will be kind of rigorous with, do you have your goggles on? Do you look like you know what you're doing? I don't mind answering questions, but when the lab starts, I will sort of direct you where all the stations are, and I'll quickly review what has to happen in each. But again, after all of that, if you still don't look like you know what you're doing, I'll ask you to sit outside. because I don't want anybody getting hurt. Any questions? Yeah.
In the lab report, you typed out.
You can type the lab report out, I just don't want the data table typed. Yeah. Work together on the lab report. Remember I said back in September, October, don't be a terrible lab partner. Don't show up not knowing what you're supposed to do. Because no one's gonna wanna be your partner. And if no one wants to be your partner, I'm not gonna force anybody to be your partner. And that might mean if no one wants to work with you, you don't get to do that. Yeah.
For reaction 7, you said to follow the steps for reaction 5, is that right?
Sorry?
When you said like the steps for the reaction that was added,
Yeah.
you said, did you say it was reaction
Same as
5?
for 5, yeah. In other words, don't use 2 test tubes, okay? And it doesn't matter what you put in the test tube first, whether it's the acid or the sodium carbonate. I'd probably add the sodium carbonate first. Any other questions? Now, I see you again on Friday. By Friday's class, I will be able, I think, to comfortably finish 4-6. We're gonna start it in a few minutes here. But if there's any further questions on the lab after you and your partner reading the lab handout, anything unclear, just ask on Friday, okay? I don't know what the block rotation is on Tuesday. But if it's first block is usually when people show up with their coats and their bags. Don't do that, because we're not gonna move forward. And I don't want anybody tripping on anything while they're carrying the chemicals. You can leave your test tube rack at your desk. When a reaction's happening, don't hang around the lab station unless you have to be there. In other words, if you're heating something on a Bunsen burner, obviously you have to be there. But if the reaction is happening and it's occurred, don't stand at the station to make your observations. Go back to your desk. Leave this on your desk. Carry the test tubes around if necessary. I'll have a waste container for the chemicals. The only things probably I don't want you throwing in the waste container are the wooden splits and the iron nail, because I want to reuse the iron nail. But again, I'll be like sort of explaining and cautioning and moving around as the lab's occurring. I'm not leaving town. I'll just want to give you a heads up before we get there. Okay? Let's go back to the booklet. I want to start with sort of where I said I would last time. I had asked, and I think the vast majority of students here actually hadn't done 1, 2, and 3 in the practice problems of 222 and 225. But I did ask for those of you that had, were there any questions about some of the answers? And if I remember correctly, a couple of people said that one of the answers, I think it was for number 3, said that the mass of calcium that was left over was 96 grams that they got, but in the key it said, I think 1.0 times 10 to the 2. 1.0 times 10 to the 2 is actually correct. And this is why. What's the mass of calcium you start with in the book?
150.
150 grams. Now, in 150 grams, is that the guess? That's the guess in the tens column. So, how much magnesium was consumed in your calculation? In other words, how much did you use? Obviously, we must have that to get the final answer, right? How much?
53.7.
So when you get that, you get what, 96.3? Okay. Obviously, that's not, you're not gonna round it to that decimal. But that is not the correct answer. Because this 3 is being subtracted from a guess. Okay? So this is the guess as well. Okay? So that's the last significant digit. So you got to round it. 96 is the 96.3 is the mathematical answer. But the guess is in the tens column because of this. Okay? Now, if this was that, then that would be the guess. But it's not. That's only 2 sig figs. And the second sig fig, which is the guess, is in the tens column. So that's why you have to round this to that. Okay? That's a little bit nuanced, but again, when someone said that the answer looked wrong, Sherry doesn't usually make mistakes with sig figs. So that kind of encourages me that she did. Okay. For those of you that actually did 1, 2, and 3, I think we did 2 in class. I asked you to look at some of the review questions, and not necessarily all of them, but some that were limiting reactants. You guys are in the hallway, why? Stop, why are you in the hallway? Sorry? You got cameras with you? Where are you taking them?
That's wild.
Don't walk by my class. Unless you're taking a picture in there, you're not go somewhere else. Okay? So, any review questions that gave anyone trouble? Meaning checked answers and they weren't the same. That was a good one, the sig fig one. Right? Those are things that we can always clear up and then they make more sense. Now, as I said last class, if you haven't looked at any of the limiting reactant questions in the review, please do so, because I guarantee one of the written response questions in the next test will be limiting reactant. One will be straight stoichiometry, courtesy of section 4.5. One will be limiting reactant, and another one will be either percentage purity, which we're about to start, or percent yield. Okay, so there's 3 of the questions in the written response. Okay? Let's have a look now at the second last of the last 2 topics. And that's percent or percentage purity. Percent yield isn't a difficult concept, but percent purity has proven to be challenging to some students, mostly because of the ways these calculations can be, or the variety of calculations that can apply here. Remember at the beginning of this section, stoichiometry in the real world, Sherry said that one of the assumptions we've been making up till now is that all the chemicals have been 100% pure. That's impossible. There are always impurities in a chemical reagent, even analytical or reagent grade. And we have to, why is it always find my room last? We have to take into account that if we're assuming a chemical is 100% pure, for example, using it to predict how much product we can make, but the mass that we're using in that calculation isn't all that chemical, obviously our prediction will be incorrect. So, throughout this chapter, we've treated all the chemicals involved in stoichiometric calculations as if they were completely pure. In reality, it's virtually impossible to obtain a chemical in pure form. And as I've said before, pharmaceutical companies, when they use chemicals to generate pharmaceuticals or medicine, they want reagent or analytical grade. But there are still impurities. They're trace amounts, but they would be listed on the reagent bottle. This is the percentage of impurities of these substances. Even the purest chemicals purchased from chemical supply companies contain impurities. The purity of a chemical is commonly indicated as percentage purity, usually by mass. So, mass of the pure sample, mass of the pure chemical, mass of the impure sample. Times 100%. This is always smaller than this. So the percentage is always less than 100%. The only thing that can go into a stoichiometry calculation, or the only thing that can come out of a stoichiometry calculation, is a pure substance. And that's kind of a clue as to what types of calculations we'll be asked to do. We either have to take care of the impurity at the front end of a stoichiometry calculation, or if we're told how much is produced, we might have to work backwards and find out the percentage purity of what we started with. And therein lies the potential challenge. And Sherry tells us here, there are several types of stoichiometric calculations involving impurities. The most common begin with an impure reactant. So if we look at determine the percent purity of the following. Remember, it's the mass of the pure sample divided by the mass of the chemical divided by the mass of the sample. A 4.5 gram piece of calcium contains 3.8 grams of pure calcium metal. Calculate the percentage purity. Well, that's pretty easy. Don't you guys do that? There's the mass of the pure chemical. There's the mass of the sample. 1 divided by another times 100%. We want that answer to 2 sig theta.
Oh,
84%, okay. That means that 16% of that thing isn't calcium. Now, why would that matter? Well, let's say we're doing this simple stoichiometric calculation.
16%.
Let's say we're adding solid calcium to a solution of tin 2 nitrate. And if you look on your activity series on page 175, you see the calcium's well above 10. So you would correctly complete this by writing calcium nitrate plus 10. So let's say the question was 10 grams of calcium is reacted with an excess of tin 2 nitrate. What mass of tin metal will be produced? And you assume that the 10 grams of calcium is all calcium. But it's not, because it's only 84% pure. So only 8.4 grams of that calcium is gonna replace tin, right? So if you dutifully draw the mole hills, and you go grams, moles, 2 grams. If you use 10 grams there, your answer is going to be wrong. The only thing that you can put in here, the only thing that's going to replace tin is pure calcium, not the impurities. So what you have to do at the front end of this calculation, you have to find out at 84% pure how much is actually calcium. So what goes in here is only 8.4 grams, not 10. So that's what I mean, the only thing goes into it is pure. Okay? Now, how could it be worded a different way? Well, let's say that we were told that a particular mass of tin was replaced from an 84% pure sample of calcium. When you go backwards, the only thing that could have replaced the tin is pure calcium. So when you get the mass of calcium you would have started with, okay, if you knew that the percentage purity of the calcium was 84%, you then have to calculate, well, what was the mass of the sample? Because some of it wasn't calcium. But the only thing that can produce tin is pure calcium. So in this scenario, the only thing that comes out of the stoichiometry calculation is gonna be the pure substance. So what you're getting here is the mass of the pure chemical. And if you knew the percent purity, you could then calculate what much the mass of the sample. And all of that can come from this. So the first type of calculation we talked about, you have to find that before you can do the stoichiometry, right? Agreed? But let's say the reaction was, the question was written in reverse. This many grams of tin was replaced from a solution of tin 2 nitrate by an 84% pure sample of calcium. So when you work all the way back, you find the mass of the pure calcium. You know the percent purity, so you would have to calculate this. How would that be calculated? Well, that equals this divided by this as a decimal. So obviously, the mass of the pure sample, which is what you calculate, divided by 0.84 will give you a number bigger than this, right? That will be the mass of the impure sample. And that's, depending on how they're worded, sometimes the stuff can be tricky. Let's look at number 2, or B. Pure phosphorus makes up 17.5 grams of a sample. There's the mass of the chemical. There's the mass of the sample, 17.5 divided by 20. Whatever 17.5 times 5 is the percent purity. Okay? But number 2 is a little different. What mass of pure potassium is contained in a 0.90 gram piece of 90% pure potassium? So in this, in number 2, they give you this, and they give you this. You have to calculate this. So that means you've got to multiply the percent purity as a decimal, either 0.90 or 90 divided by 100, same thing, times the mass of the sample. Okay? And I think that's going to give you what? 0.81 grams? Yeah. Yeah.
When you're writing like the equation for question 2, would you want to put a variable in the place of what you're finding, like say the mass of the pure chemical X?
You could, as long as it's clear what the variable is. Okay, so in other words, if you're using X, then as you maybe learn in math, if you use a letter, tell me what that is. Let X equal, okay? That type of thing. Now, Sherry gives you a heads up that there is variety in these types of questions. She gives you 2 here, just to give you an introduction. What mass of sodium hydride can be formed? And when she uses the word combination, that means synthesis. Of 15 grams of 80% pure sodium with excess hydrogen gas. Now, if it's excess, it always means it's not part of the calculation. So that means that's the limiting reactant. And by the way, I won't mix limiting reactant chemistry with percentage purity. Okay, I'm not going to do that. So, remember, as I've said before, hydrogen's in 2 places on the periodic table in your book. It's over the alkali metals. It's not a metal, but it forms a 1+ cation when it reacts with some nonmetals. So also over the halogens, because it forms a 1- anion when it reacts with metals. So when sodium and hydrogen react, we get sodium hydride, 1+, 1-. Okay? And it's a solid, as all ionic compounds are. So based on the information, there's the balanced equation. Okay? Now, if we used all 15 grams of the sodium sample to calculate the mass of sodium hydride, we'd be wrong, because it's only 80% pure. So if you look at number 2 in the practice problems we just did, she said, what's the mass of the pure sample? She asked you that because that's what you have to do. You have to find out how much sodium we actually have before you can do the stoichiometry. Meaning, the only thing that goes into that has to be the pure substance. So, the first thing you have to do, either 80 divided by 100 or 0.80, doesn't matter. That's the mass of the pure sodium. Once you're there, this is moles, grams to moles to moles to grams. The only difference is, you gotta find out what you're starting from. Is that reasonable? Now that's the simplest and usually the most common type of question. But it's not the only type. Look at this one. What is the percentage purity of a 7.5 gram sample of sodium metal that formed 7 grams of sodium hydride when reacted with an excess hydrogen gas? In other words, you're told what it formed. Now remember, you can only get sodium hydride from pure sodium. So forget this for a second. The 7.5 gram sample has the impurity, but you don't know how much. But again, the only thing that comes out of a stoichiometry calculation is pure. So what you're actually calculating here, the first thing is, what mass of pure sodium would have been able to make that mass of sodium hydride? So you start from the grams of sodium hydride to moles sodium hydride to moles sodium to grams pure sodium. So you calculate the mass of pure sodium that would have been required to make that mass of sodium hydride. Now that mass of pure sodium, as you expect, is less than the mass of the sample because it wasn't all sodium. You have the one on the bottom, you have the mass of the sample. Stoichiometry has given you the mass of what you would have needed to make what we made. So now you just 6.7 grams divided by 7.5 grams times 100%, 89%, okay? Now, two different ways it can be worded. Actually, there's more than two, but it's all based on the thing that the only thing we can calculate is pure. We can only go into a stoichiometry calculation of pure. The only thing coming out of a production question is, well, the only thing that could have made that is pure sodium. So we gotta work backwards to find out how much of the pure substance we really have. And in the first question, we gotta begin with how much of the pure sample we actually have. Make sense? Well, let's see. She gives you 3% purity questions. Let's pick one. Now here's the thermite, except that should be liquid. That should be liquid. Because that's low above the market, both of those things. The thermite reaction is extremely exothermic, producing temperatures in excess of 2,500 degrees Celsius. These high temperatures were used to weld iron tracks together during the early days of the railway. They still use it to repair tracks today. Thermite's eventual power as follows. There's a balanced equation. If 2.44 grams of 95% pure aluminum is reacted, how many grams of aluminum oxide can be produced, assuming you have excess iron free oxide? Well, this is the same as the first sample. If 95% of that is pure, 2.44 times 0.95 gives you the actual mass of aluminum. Pretty straightforward. I like number 2 though, that's a bit different. How many grams of 73% pure iron-free oxide are required to form 24.5 grams of pure white-hot iron metal, which by the way would be liquid in a thermite reaction? Hint, begin by determining the mass of pure oxide required. Because we can't make this, we can't make iron unless we're using pure iron-3 oxide, right? So basically we're asking what mass of pure iron-3 oxide would we need to make that? When we have that, we know the percent purity, we know the mass of the sample, or we know the mass that we need, And then we basically divide the mass of the pure iron 3 oxide by the percent purity expressed as a decimal. Try out, try number 2. You're still gonna need the balanced equation, you're still gonna do stoichiometry, but you start with the stoichiometry, and that's what she gives you here. What mass of pure iron 3 oxide would be required to make that much iron? And then once you have that, then you go back to the equation for percentage purity. What do you know, and what do you have to calculate? We have recess after this block, right? Okay.
Did you find the balance equation?
We got to 11:30.
I don't know. We gotta do the stupid shit. What's it called?
I don't think I'm gonna help you with it. I expect you to have a little difficulty with it. So the first calculation is just section 4.5, straight stoichiometry. You're calculating how much pure iron 3 oxide you need to make that much iron.
Don't you just go? I forgot you gotta do. Start with the equation and the balance equation. Shit, I forgot. How is this day?
So once you get that, we'll stop for a second and I'll tell you what to do, all right? You know the mass of iron we produce, we have the balanced equation, so we go grams to moles of this to moles that to grams that. First calculation could be, that could be the first question on the test, straight stoichiometry, for the first stoichiometry question. Adding the second part to it elevates it to the percentage purity. And we want our answer to 366. Anybody have this yet?
About 35.
I'm off by
Or zero,
I'm off by 3%.
Three sig figs,
yeah,
35,
it was 35.02.
okay, so let's just go 35.0.
Yeah.
Anybody else get that, 35.0? Okay, so what is that? That's this. Okay? In other words, only that amount of pure iron 3 oxide can make that amount of iron, right? Whatever isn't iron 3 oxide can't make iron. So we've got this. We've also got this. Okay? So right now we have 73% equals, what did you put, 35.0? 35.0 grams of pure iron. Pure iron 3 oxide, sorry. And we want to know the grams of the sample. Well, if we divide this and this by 100, this becomes 0.73, doesn't it? Times 100%, divide both sides by 100, we get this, right? 0.73. So this mass of sample has to equal 35.0 grams of iron 3 oxide divided by 0.73. Correct? Obviously, something divided by less than 1 is going to give a bigger answer, right? And grams, you don't want them to go away. You want them to stay there because we want our mass in grams. And actually, that's 0.730. My bad. Should be 3.6. Okay. And then that's your answer. Everyone see that if we divide both sides by 100, we get 0.73 equals that over that. Right? And to get this, we gotta divide this by this, right? There's no units in a percentage, it's just a number. So those units stay put. And I don't know what the answer is, but that should be correct. Problems? You gotta have your head in gear. I get that. Now, there's one more question there. We're almost out of time. I meet you guys one more time. As far as I know, is Friday a full class? Oh my God. Okay. How about we'll start Friday with try number 3, check your answers. Find percentage purity questions in the review. Try some of those and check your answers. And that's how I'll begin Friday's class. Any issues with number 3 and or percentage purity from the review? Then I'll do percent yield, which is going to take no time at all. Percent yield's easy. And that might mean we might even be able to squeeze in a little review on Friday, who knows? But we also maybe have to allow some time if there's any issues with the lab work. Okay? Did I go too fast? You guys okay with that?
Is our data table due next class?
What?
Our data table for the lab?
No, the data table is only when you walk into the lab.
Oh, okay.
Yeah, so I'm gonna come around. Again, the only thing gonna be in your desk is gonna be your lab handout, your data table, something right. No bags, no books, right? But I'm just gonna come around with a little pen and initial all the data. And I'll probably do that as you're doing the lab. I'm not gonna like take 10 minutes to initial everyone's data table. I'll just go 1, 2, 3, 5, 6, 7, 8. If we have on that day an odd number of people, I'm not sure if we even have an odd number regularly, but if there is an odd number of students doing the lab, that means one group of 3, not any more than one group of 3. Because 2 groups of 3 is 3 groups of 2. And you can't do the lab by yourself. And if by some unfortunate circumstance your partner is sick on that day, you might have to join us. Okay?
No, I won't be sick.
See you Friday.